next up is the direct comparison test. The idea behind the direct comparison test, is taking it from its name, is to literally directly compare two series. All right. So we start with the series that we're trying to determine whether or not it converges. All right. And we're going to call that series A sub n. Okay. We're going to directly compare that series with another series. All right. One which we already know whether the series converges or diverges. All right. So here's the idea. Let's go with the convergent part first. If we've got a second series, one that converges, we'll call it C sub n there. All right, since convergence begins with the letter C. Okay. If the converging series has terms which eventually, maybe not right away, but eventually, the terms of the converging series are larger than the terms of the series we're curious about, well, then it's guaranteed that our series is going to converge as well. Okay. In essence, the convergent series is an upper bound of what our series is going to add up to. All right, and if the upper bound converges, well, then our series must converge as well. Let's just say that we have our series of 4 plus 1 plus a quarter plus a 16th plus so on and so forth. Now this is a geometric series and r is less than 1, so it converges. But let's just say that we didn't know for a fact whether or not this series converged or not. Okay, but we do know another series which does converge, all right? And the series 3 plus 1 plus a third plus a 9th plus a 27th, we know that that series converges, okay? Well, what we can say here is, since this is our C sub n, okay, that's the series that we know converges. This is our A sub n. We don't know whether it converges or not, so we got the question mark there. Now, initially, A is larger than C, all right? Then they're equal to each other. But eventually, the terms in C are larger than the corresponding terms in our unknown series. What does that mean? Well, C converges, and C's terms are larger than A's terms, all right, eventually. So therefore, this series must converge as well. All right? And we can actually prove that it converges with the geometric series test. But again, just kind of working with a basic example here. All right? If we go in the other way, let's say we still have our unknown series A sub n, and we have a divergent series, D sub n. Right? Well, if our terms of our unknown series are bigger than the diverging series, then we know that the series that we're curious about must also diverge. Okay? In essence, we're talking about the converse of what's happening over here. Okay? The bigger numbers must also diverge, since the smaller numbers that we're adding together diverge as well. And that's the idea behind the direct comparison test. Take two tests that you know about, one test that you know about and one test that you're curious about, and compare them. And if one converges and is bigger than the one we're curious about, the one we're curious about must also converge. If one diverges and the smaller than the one we're curious about, then our series must diverge as well.